In this slide, we will start talking about the systems of nonlinear equations. And up to this point, we focused on the determination of the roots for a single equation. It was just one single polynomial. But now there are nonlinear equations, multiple of them. You can see here that one is this and up to n equations. The solution of this system consists of a set of x values that simultaneously result in all the equations equaling 0. So we try to have all the equations become 0. And for that, we need to solve them simultaneously. So if the simultaneous equations are linear, meaning that the polynomials have only linear, so the power is 1, the linear values of the variables, and b and a's are the constants. These are called linear functions. But if we have a different power other than 1, like this, you can see x squared, y squared, these ones, then these are nonlinear equations. And for these, we need to have these equal 0 to be able to find the root. That's why we convert these by isolating one side to be 0, like this. And for example, if we have 2, we can say this is u and this is v function. Simply we can have this kind of representations of these nonlinear equations. And the solution would be the values of x and y that make the functions u and v equal to 0. Here we can use the open methods to be able to predict the roots of these. Fixed point iteration and also Newton-Raphson we can use, and we will show these in the following slides, starting with the fixed point iteration. In this slide, we will check the fixed point iteration method for nonlinear equations, multiple nonlinear equations. And if you remember, for only one equation, the fixed point method was actually like we were using an xi value at one side, and the other side was a function of xi. We will simply extend this into multiple equations. And if we have like two equations, for instance, then the first one can be equivalent, can be written in terms of the first variable, and the second one can be written in terms of the second variable. And we will already have the same number of variables as the functions, the number of functions. That's why if we have two functions, we will have two variables, unknown variables. So we need to find these. And for that, we use the first function as xi plus 1 is equivalent to fxi, which is similar to this actually. But the second one should be written in terms of the second unknown variable, which is y here, for instance. yi plus 1 is equivalent to fyi. These f functions can be different. And for more than two equations, for example, if there is 3 equations that can be a z as the third unknown variable, then the f function should be in terms of z. This process can be repeated up to n number of nonlinear equations. And we can try to solve these functions to be able to find the roots. But this fixed point iteration has one important shortcoming and issue for multiple nonlinear equations, and it is that the convergence often depends on the manner in which the equations are formulated. You know, these equations can be formulated in different ways, and the manner of formulating these actually influence the convergence. So also even those instances in which the convergence is possible, so let's say we were able to obtain functions where we were able to get convergence for the results, the divergence can still occur if the initial guesses are insufficiently close to the true solution. So the initial guesses are important. Which values you choose is important. They should be close enough to true solution so that you can get correct results. And because there are many like unknown variables, it is not easy to make all of them correctly goes to near to the true solution. That's a big issue. And there is a sufficient condition for convergence, for example, for the two equation case, and it is that the partial derivatives of the first function, this is u actually, and the second function here for this, the partial derivatives in terms of x and y, the unknown variables, the summation of them should be less than 1 for the absolute values. Here the same for v function as well, should be less than 1, the summation. These criteria are so restrictive. They restrict our actually solution process a lot. And that's why the fixed point iteration has limited utility for solving nonlinear systems. However, as we will describe later, it can be very useful for solving linear systems. So this is pretty handy for linear systems. But when the functions are nonlinear, this issue, this restrictive issue can be a big problem to solve these. That's why we prefer this for linear systems. In this slide, we will have an example for the fixed point iteration for two equations, two nonlinear equations, and see if there is any issue with this. Here we have two functions, as you can see on the right hand side, the u function and v function equivalent to 0, these ones. And the roots, the correct roots are 2 and 3, we know those. But actually, in an actual case, we don't know them, and we want to use the numerical method to predict them. And the question says, let's start the guesses as 0.5 and 3.5. So let's first formulate these functions as the first one will be in terms of x, the second one will be in terms of y. And in the first one, we can simply isolate this x and have a function. So the first function is, if we isolate x, it is x squared, actually 10 minus x squared divided by y. So we simply isolated this x here and divided by y, that's why. And in here, of course, this is xi plus 1, and these are I and I. We can do this way. So actually, what we did was we just wrote xi plus 1 in terms of gxi, like this. The y can be there because there is no running away of disappearing it, actually. So it has to be there. And the second equation will be from the second one. In here, we will this time isolate y here. This can be simply isolated, just move the rest to the right side. And then yi plus 1 becomes 57 minus 3 xi yi square. So this became yi plus 1 is equivalent to gyi, or these can be g1 and g2. Okay, we wrote these. Now we want to solve these. Initially, there are two options here. You can say that, okay, this will be I over here, or because here we will find an I plus 1 value, we can simply use this in the second one as I plus 1 to have a quicker convergence. So in here we can say, if we are using this in the second way, as a second equation, we can say this is, okay, let's make this I plus 1. This can be easier. Then let's use the first one, first of all. If I equals 0, let's have this in a bracket like this. And let's start with I is 0. Then we know that x0 is 1.5 and y0 is 3.5. Then from the first function, x1 is equivalent to 10 minus 1.5 square divided by 3.5 square. And this becomes 2.21429. So what I meant here by using this was using this value, because now we know the second guess, actually I equals 1, the guess for the I equals 1, then that's why we can use this in here instead of using the initial guess, and we can maybe approach faster. That's why this is recommended by the book as well. So then we use the second equation, y1 is equivalent to 57 minus 3, now xi plus 1 is 2.21429 times yi is y0, 3.5. Here y1 becomes minus 24.37516, and here even you can see, okay, x1 is 2 and it's getting closer to this, but y is minus 24. It's getting away from this. Seems to be diverging. Let's see if it is diverging in another iteration and be sure that it's diverging, so then we can say we shouldn't use this initial guesses or this approximation maybe. Let's make I equals 1, and we know that x1 is 2.21, 429, and y1 is now minus 24.37, 5.6. Then x1 is equivalent to 10 minus xi, meaning actually this is 2, I plus 1 here, and xi is x1 2.21, 429 divided by yi, it's minus 24.37, 516. Then x2 is equivalent to minus 0.20910, and unfortunately, because the y diverged, x is now diverging too. Instead of going 2, it's going to a small value. Now let's try the second one, the y2 equation, and it's 57 minus now 3 times this 0.20910 times yi square, and yi is minus 24.37516 square, and the result here is 429.709, and you can see that both of them are diverging. And this is the issue that we mentioned in the previous slide. We said that for the nonlinear multiple equations, we can have an issue of divergence for the fixed point method. That's why this is useful for linear equation. If this was only x and this was only y with no square, this wouldn't be probably diverging. It was converging actually, but because these are nonlinear, it is diverging. You can check a linear function as well to understand this, but let's continue on this in another way. So we actually formulated these in this format. Maybe we can change the formats of formulations, then we can have a convergence. Let's see that in the following slide. In this slide, we continue to example 611, but we want to use a different format of formulations to represent them in the fixed point iteration. Remember that the u function was x squared plus xy minus 10 equals 0. Then maybe from here we can have a different formulation of x. We can simply isolate x from this. In that scenario, xi plus 1 will be just so 10 is moved to the other side, xy is moved to the other side as well, and we take the square root and it becomes xi plus 1, and these are xi, yi. This is the first function, and the second one was v xi xy was equivalent to y plus 3xy square minus 57 equals 0, and in here now we are using this squared value as well, isolated. If we isolate that, yi plus 1 it becomes, and it is 57 is moved to the other side, y was moved to the other side as well, then divide by 3 times x, and again take the root square. Here yi and x is xi plus 1, because we are guessing it here already when we use this in the first place, then we can use that here. Now the results will be better. Let's check. I equals 0, then xi is, as x0 is 1.5, the initial values, and y0 was 3.5 if I believe. Yes, y0 was guessed as 3.5. Then use this in the first function. Then x1 becomes 10 minus x0 1.5 times y0 3.5, and the result is 2.1795. You can see the actual value was 2, so it's converging to that, it seems, in the first iteration. Let's use y1 as well. It is 57 minus yi, which is y0, 3.5, divided by 3 times, and xi plus 1, 2.17945. And if we calculate this, it becomes 2.8601051. See, these are close enough to the true values, it seems. So let's continue one more iteration and see it really goes to the actual values, like converging to them. For this, x1 is 2.17945 and y1 is 2.86051. Then let's start with x1, sorry, x2 this time. Square root 10 minus 2.17945 is x1, and times 2.86051 is y1, and the result is 1.94053. You can see it's getting closer to 2. The actual values, x true was 2 and y true was 3. So we want to approach to these, and it's getting closer actually. So we continue with y2, and it is root square 57 minus y1 2.86051 divided by 3 times x2, 1.94053. From here, this becomes 3.04955. You can see it's getting closer to this as well. So it's converging, basically. These are converging. Maybe we can continue more, and it will converge to actual values. So, as we said earlier, having a different formulation from the same functions can change the things, and it can result in converging. Especially, the fixed point iteration works with the linear functions, as you can see here. If there are linear terms in the function, then it will be very good to be able to converge to a true function.